And I have the honor and, as I read his bio, the extremely humbling task of introducing our next speaker, Dr. Mark Cassidy from the University of Western Australia, where Mark is the Australian Research Council Laureate Fellow, the Lloyd's Register Foundation Chair of Offshore Foundations, and he's also the Director of the internationally known Center for Offshore Foundations at that institution. In addition, I guess they didn't feel Mark had enough to do. He was recently named the Deputy Director of the Australian Research Council Centre of Excellence for Geotechnical Science and Engineering. Mark's background is that he attended the University of Queensland for his undergraduate degree, and then as a Rhodes Scholar attained his doctorate at the University of Oxford in the late 90s. His research interests are, as you probably see from the title, are in offshore geotechnics and engineering. His specialty area in particular is in developing wave structure soil interaction models and their impacts on offshore structures. As a result of this research, he's published over 160 refereed journal and conference papers and jointly holds 2 international patents. He has been named a fellow of the Australian Academy of Technological Sciences and Engineering and Engineers Australia. So perhaps you can see why we were so excited when Mark graciously agreed to make the trek from the other side of the world to come and grace us with his talk. Please join me in welcoming Dr. Mark Cassidy.
Thanks very much, Tom, and thanks very much to Tom and to Jeff and to Anand and the rest of the organisers of Geo-Congress for this invitation. Very kind invitation. I'm sort of regretting taking it now. I mean, I really enjoyed Bill's talk. I don't know if you have this analogy, but I feel like he's thrown me a hospital pass, and I'm going to do my best Upton Sinclair impersonation to try to justify my career. But the argument I think I'd like to, I agreed with what Bill was saying. The argument I'd like to add on top of that is this one, is that the world's demand for energy continues to rise unabated. You might, in the US, be on 5 planets. Europe's on 3, is it? And I think Australia, well, I like to think we're a little bit better. We're probably at 4.9. And we have actually, in Australia, started to decrease our energy. And it's actually surprising why. Well, it's not surprising. Electricity prices have gone up, and then people have stopped using it as much. It's been that simple. Nothing to do with Priuses, but to do with the fact that demand side prices went up, people started using electricity, yes. However, in this world, we've seen a doubling of energy demand over the last 3 decades. And when you consider that the vast majority of people in this world live with very little energy, and I would argue have a right to have the energy that we have and the lifestyle or the opportunities that we have, that this, I think, is going to continue into the future. And this creates a great challenge. The ocean environment holds a lot of solutions to this. And I would like to add to Bill's talk that I think there are still a lot of geotechnical engineering challenges there, and there's still a lot of opportunities technically as well for geotechnical engineers to solve some of these problems. I'm not sure this analogy is quite right, that we were part of the problem in the first place. Maybe we're also going to be technically part of the solution. So today's talk, in that light of this, there's this increasing demand of energy. My co-authors and I sort of looked at 3 areas which is changing geotechnical engineering practice. And they're in this ultra deep water. We're moving into, or we have moved into water depths greater than 1,000 metres for oil and gas developments, into new regions. The one I'm going to concentrate on is the one closer to my heart, around Australia and the Pacific, though the Arctic is, of course, another major development area for oil and gas. And also, in a world of climate change, geotechnical engineers have opportunities to develop renewable energy solutions. And so that's been a great area of development in our profession in the last decade or so, and will, I think, increasingly be so into the future. So what I've done in this talk and in our paper is to take a very bird's eye view of these 3 issues and look at example challenges that that's giving our profession technically. And then in this talk, not only will I give the bird's eye view, but I try to go through 3 specific examples where I try to show how we've actually implemented some technical change in those areas. So starting off in deep water, with this energy demand and resources have been dissipated in shallow waters, the oil and gas industry has moved into deep waters off the continental shelf into water depths now exceeding, say, 3,000 meters here in the Gulf of Mexico and places like Brazil. And that's changed the type of structures that we've been building from, if you see on the top left-hand side here, fixed platforms where very rigid connections through, say, truss work legs all the way to the seabed, where you probably use a traditional type piling type method, through to now in deep water where we have floating facilities that are moored with large anchors and have pipelines that link the reservoir to manifolds and then rise up to the floating system. The left-hand slide here is a schematic of a development now in Australia. The Gorgon development is off the continental shelf in 1,300 metres water depth. And just showing the examples of what we need to design now, including things like mud mats to hold the pipeline systems on very deep water. These are like shallow foundations in very soft soils. The pipelines themselves, if they turn the gas on and off, heat up and or cool down, they expand and contract, and that moves these manifolds around. So we're now moving into a regime where you're actually designing things to move more so than just designing things to stay fixed. Another example of a moving type design that's recently been done in Australia is the one shown on the right-hand side. That's the Sydney Opera House, to try to show the scale here of a pipeline that had to come up the continental shelf for the Gorgon development, and so it had a span of a couple of 100 metres. And how do you design that pipeline as it's bouncing around the seabed? Deep water has also changed and brought up lots of different types of anchoring solutions, lots of innovations from suction caissons in the top right-hand side here, through to the example I'll show, which is plate anchors, to drop anchors. It's like playing darts with the seabed, where you put a big dart down and you drop it in and let it flow through the water and then penetrate the soil. Great challenges on how far will it penetrate to, how does it mix and infuse the water as it's doing that, changing the soil properties, and then what's its capacity afterwards. So if I had to sort of look at the challenges, I mean, the environment's characterised by very soft soils, normally consolidated or lightly over-consolidated soils. And the challenges are, in all offshore, there's great costs in site investigation, but particularly so in deep water, where one is very interested in things like anisotropy, degradation with cyclic loading, and increasingly focused on just the top few metres of the soil. How do we characterise just the top metres of a very soft sediment? As I mentioned before, there's a movement away from traditionally what we do is design for keeping things stable and still, to having to design things that are mobile. And therefore we get large deformations. How do we analyse that? Even changes in seabed topography. We've got pipelines that slide back and forth, sort of ploughing up the seabed. How do we design for that type of movements? Cyclic loading, and now also increasingly a focus on stiffness and not just on capacity. Just some example solutions. Much improved in situ technology, and some people in the room have been responsible for a lot of this, including the Norwegian Geotechnical Institute has a very large diameter piston coring system, and also it's been dear to the heart of Mark Randolph, EWA, is like continuous flow round penetrometers. So these are things like balls on the end of a stick that you move up and down, and so you can look at things like rate effects and degradation of soils with cyclic loading. Things in bold here is going to be the example I'm going to show. There's also been in the offshore industry a strong movement towards writing failure envelopes for combined loading directly in terms of the loads that are being applied, the vertical, the horizontal in the moment. So sort of throwing away these sort of inclination factors and shape factors that we traditionally teach in geotechnics, because they're more accurate and because, as I'll show, they can be put together in plasticity models to look at displacements as well. And I'm going to show that for the SEPLA anchor, which I'll describe in a minute. So here's a SEPLA. It's a plate anchor, which they put, they insert it in the bottom of the tip of a suction caisson. And so they install the caisson like so. They put a suction pump at the top of it, and it sucks itself into the ground, which delivers the plate anchor to a certain depth, but unfortunately delivers it to it in a vertical plane. They then pull the mooring line up, which will rotate the anchor around until it becomes more normal to that mooring line. And that's called the keying process. When it does that, it actually moves itself up and it rotates around. And that loss of embedment is very important for the industry because deep water sediments are increasing strength with depth. If you lose too much embedment or you don't know what that embedment loss will be, you don't know how to predict what the capacity of the anchor eventually will be. So there's been an industry requirement to come up with better keying models and to be able to determine how far it will move up. And then further on, once you've got it in operation and you're sustaining it or you're cyclically loading that anchor, say in a big storm, what sort of load can it sustain? So we did a big project for ExxonMobil out of Houston, and coming up with this model for keying, we developed what I call a force resultant model. And the key here is it's like all plasticity. What we try to do in this case is write a yield surface for the anchor directly in terms of the loads applied. And the way we do that is to, in this case we did a 3D finite element analysis. You can see inside that green mesh is a shank and a fluke of the SEPLA anchor. And in the finite element, you can say move the anchor down or sideways or rotate it or do all combinations of that. And you get different load paths, which are shown here on the blue lines. They're the load paths up till failure, and the dot's the failure point in a numerical analysis. We can then join all those failure points together and define a yield surface or an ultimate capacity surface for that embedment directly. And that's what it would look like, and we can put a formula to it. And there are the bearing capacity factors uniaxially for that anchor itself. So that more accurately defines what's the capacity there. But in this case, we want to see what's the movement going to be. So we have to assume some sort of flow rule. In this case, we're assuming associated flow. So the movement, once it's onto that capacity surface, the movement will be normal to the surface itself and has some sort of hardening, i.e. the surface shrinks as it comes up with lower shear strength and increases in size with higher shear strength, remembering that's an increasing strength with depth profile. And in the end, we can put it together in a model in a simple spreadsheet type approach. Here's an example. It's a 20-metre embedded SEPLA anchor being pulled with that load TA. That's from the chain, increasing strength with depth profile. We're basically trying to, at each step, predict where this will move to. And so here are some example results for an anchor that's being pulled at 90 degrees up by the chain. It sort of moves itself around in horizontal. So here's the horizontal vertical displacement. So it moves itself up and around as it twists into position until it's finally twisted all its way. It's even rotated a bit further here because the offset was not in the middle of the anchor to about, I think it's about 11 degrees off that offset until you get no more rotation of the anchor. So you can believe it's fully keyed in. At that stage, it will just start to pull itself out. And so this type of modelling can give you a good prediction of that type of keying behaviour. On the right-hand side is the normalised chain load against that loss of embedment. And one can see that at the current depth, so that's if you normalise by wherever the anchor is as it's coming up, one sees a bearing capacity factor a bit over 12. You remember it was 12.7 for just pure vertical load. It's a bit less than that because it's still got some horizontal load as it's pulling out. However, if you normalise by where the undrained shear strength was at the embedment that the SEPLA was, you're getting about a loss of about 20% in capacity. And that's the sort of figure that's really important for the designers to know what that is. These modelling, we could look at different angles. Here's something at 40 degrees, which is more realistic for the type of application that this anchor would have, and with different configurations of shank. And so in this project, we could show that the loss of embedment for most conditions was between 0.5 and 0.9 widths. We also did experiments of this, and we could show that if you installed the anchor, took away the caisson, and let some reconsolidation, so waited some time, let the excess pore pressures that had been developed dissipate, you could reduce this loss, obviously because you're getting increasing strength. And interesting, and part of this project is that we worked out that this design of the anchor was completely wrong. It has this flap you can see on it. And the idea of the flap was it was supposed to, as it was keying, open up to try to stop the keying, to give more sort of horizontal, to stop it sliding upwards. And then it was supposed to close once it had been keyed into position for full capacity. Unfortunately for them, it did completely the opposite. It stayed closed when it was keying up, and then opened up when it was trying to be in operation. They just basically had the hinge on the wrong side. So by investigating the mechanisms that were occurring, we could show that to the designers and change the anchor design. Going on to operational issues, the little movie here is our beam centrifuge at the UWA. For those who maybe have not been exposed to the centrifuge, we spin soil at large accelerations, the idea being that soil is a frictional material, and to get the scaling between a small-scale model and the larger prototype offshore, you need to accelerate gravity to make sure the stresses that are occurring under the model are scalable. And so in this case, we were spinning at 150 times gravity, so we could shrink our 8 meter by 5 meter SEPLA down to the one you see there on the left-hand side, a 1 in 150th scale model. We're using West African soils that have been collected off Angola. And the idea here was to look at the sustained loading after it's been keyed in. So here, if you just look at this graph, the idea is that we key, this is all the keying process, and we got to a stage here where it's been keyed in, and then we hold under a sustained load. And we hold it a load that is lower than what it would have just been if we just kept pulling it out. And that's kept pulling it out in an undrained sense at a certain rate. We hold that load, and then we let the pore pressures dissipate. We're measuring that to either 50% or fully dissipate, and then we pull it out to see what increasing strength we get, or whether we can just continue to hold that load. And here's the summary of this type of results. So if you see here on the x-axis, this is the sustained loading against what is the maximum monotonic pull-out at a certain rate. So if you took the 60% case, you're holding it 60%, and letting it dissipate by 50% of the excess pore pressures, we could have an increasing capacity of 20%. 100% was to 1.6, so 60% increase. 70% you get increasing capacity. However, there is a threshold that you can do this to, where basically if you try to push your luck too much under sustained loading, you actually pull your anchor out. And this is because the failure is determined between a balance between the increasing capacity you're getting under consolidation. As the excess pore pressures are dissipating, getting consolidation in front of the anchor, increasing capacity. But you're also getting a reduction in capacity because it's slowly bringing itself out under that consolidation. And because the rate is slower, the strength of the soil is less, and therefore you can get to the case where it just slowly pulls itself out rather than being able to sustain its consolidation in front of it. And that happened for these soils and this anchor to be at about 85%. Cyclic loading, the same processes are occurring. You're getting consolidation in front, but the level which you can go at is lower, it's at 75%. So the left-hand slide here is you could actually cycle up to about 0.75 of that monotonic capacity, and it would be able to hold itself over repetitive cycles. However, if you went above that, the cyclic loading was doing more damage to the soil, and you couldn't hold it. And you could see on the right-hand side there, it's just pulling itself out. And these were sort of important for the Exxon engineers as they wanted to come up with a design methodology for using these type of anchors for permanent installations. And the reason they want to do that is that they basically take vertical load very well. So you can put a taut mooring in. So the angle up to the floating platform can be at about 40 degrees, get much lower footprint, and you get much greater advantage in having less sort of footprint for your development. For this example in Deepwater, I'd like to move to new regions. And as I said, I'm going to concentrate on Asia and the Pacific. And sort of the reason being here, this might scare Bill a little bit, but this is sort of a slide I use a lot in Australia to show that our region, there's still a lot of untapped gas that is uneconomical to develop technology at the moment. So this slide is showing that the solid graphs here are where it's economic to develop the oil and gas. You can see the Gulf of Mexico, they're mostly filled, whereas the shaded areas where it's still uneconomical with existing technology development. And you can see there's a very large red section, which is untapped gas or stranded gas in Australia. If you looked at in our region of Australia and also Asia, we have very stratified seabeds, carbonates, sensitive silts, and this is sort of the genesis of why we've got a research group out in Perth. Things like understanding drainage conditions, rate effects, compressibility, cementation. These all caused problems when they tried to pile the Rankin B and the Goodwin in the 80s and 90s in Australia. The other challenges is that we're very remote and very long distances. For instance, we've got a pipeline that's going to be over 850 kilometres in length in Australia at $4.5 million per kilometre. So you've got a lot of potential to make savings as a geotechnical engineer. And we have very layered conditions, and installing platforms, like I'll show, in those layered conditions can be very difficult. Some solutions are improved numerical methods for rate effects, for soil softening, including sensitivity and softening in our type of modelling. And again, I've showed an example of strength through consolidation. Pipeline modelling has become quite important. We've had significant savings. And there's also been an emphasis on more direct predictions using in situ CPTs and other devices directly into design. And the example I'm going to look at is a punch-through modelling for mobile drilling platforms. But before I do that, I just wanted to, this wasn't in the paper, but I thought it was important to come to America and maybe describe this. This is a really new development in the Australian industry, and it's got interesting sustainability questions, which I hopefully can add something to this discussion. As I showed in the first slide, the traditional way of developing gas is to have a floating platform or just have a pipeline that imports it back to the shore, where you'll put a processing plant to basically, big refrigerator, to liquefy it and then put it on a ship to export or put in a pipeline. Most of Australia is exporting in ships. However, this development's called Prelude. It's just been built, it hasn't been placed in position. The bottom left-hand side is in the shipyards in Korea. The idea here is that they're going to do all this refrigeration offshore. So it's a big boat that you can do all the processing offshore. You don't need a pipeline to go back to shore. You don't need a processing plant onshore. And it's causing a lot of controversy in Australia for very interesting sustainability reasons. But before I discuss that, I'll just, some of the statistics here, I put it in feet, but it's 488 metres in length. So that's about 4 football fields, 70 metres in width. It weighs 600,000 tonnes. Now that's, if you've ever seen an aircraft carrier, we don't have any in Australia, our Navy, but yours, that's 6 aircraft carriers in weight. There's a massive ship being developed for this. And it's going to be moored for 25 years. It's like a big vacuum cleaner. It's going to come out and suck all the gas out, process it, export it. And when it gets to sustainability, it's interesting because the Shell chairs, the Shell development, was recently quoted in Australia to say that this is a good sustainable development because compared to the traditional way of building, it's going to save 50% on materials and 90% of the impact on the seabed and other terrain. There'll be a 90% less area affected by the development. However, if you flipped another side of this, and where there's actually a lot of debate in Australia, it goes to the question that was asked in the last talk about what's the human balance here. And the Australian government and the Western Australian government is obviously very worried about that this is built in Korea, sucks gas, gets exported to China, and what's the benefit for jobs and development in Australia. And possibly more importantly, because it replaced what was going to be a traditional development, there'd already been a very large agreement between the Aboriginal communities in these very remote areas of Australia to produce jobs. It was a land rights development. And it was a multi-billion-dollar development for the Aboriginal people in those areas. And if you know anything about Australia, we're a very first world country, but we have very third world conditions in some of our remote areas. And so there's been a bit of controversy over, are we continuing to maintain very, very poor conditions for our Aboriginal people by not allowing some of these developments to come on shore and just allowing them to be big vacuum cleaners. Maybe on the environmental positive side, however, after 25 years you can take it somewhere else and continue to go, so you don't need to rebuild the ship. Okay, that's my aside on floating LNG, which you'll, I think, see a lot more of in the future. The example I wanted to show in the Geotechnics here is mobile drilling rigs. How do we install drilling rigs that do the majority of the drilling for oil in water depths up to about 120 metres? Here you can see that they're very slender platform. Leg lengths can be about 170 metres. They've got what are called spud cans, a 20-metre diameter footings underneath. These need to be pushed into the seabed as we raise the hull up off the water. And this is going to be a very tricky operation, particularly when you've got layered soils and when you've got a strong soil over a soft soil. And one can get what's called a punch-through failure, where you actually punch the stronger soil into the softer soil. And it reduces the load, and because you're holding the hull up above the water, it's like, you know, removing one leg of a bar stool that you're trying to sit on. And you can get these type of problems occurring, bent legs, and even collapse of platforms. And the industry is still seeing 1 or 2 of these types of punch-throughs per year, and particularly in new regions. Technically, what do we do? Well, as an academic, can we design better methods to analyse this type of problem. And the issue with the industry guidelines at the moment is that they don't account for the sand properties at all. So these are the new ISO recommendations that have come out. They recommend two methods. One's, you probably know these from Geotechnical Engineering School, the punching shear method, the Hanno-Meyerhof method. You account for a cylinder where you take the strength of the sand up in the cylinder and the clay below. But unfortunately, the punching coefficient Ks you need there, at least in the guidelines here, doesn't have any relationship to the sand properties. It relates to the strength of the clay, as you see in the formula below. The other option they give in the guideline is to do a projected area where you don't account for the sand at all. You just say, well, it's going to project down to the clay layer to a bigger footing below, and if you project it 1 to 3 or 1 to 5, you can get a good prediction of what the peak load at punch-through will be. Here's a little model of what we did to actually show what the mechanisms are. So this is half a spud can up against a transparent window in the centrifuge at 200 G, taking lots of photos. And on the right-hand side is the actual loads we recorded and the mechanisms that are occurring at any time. And about now was the punch-through failure, you can see, and that's the middle mechanism there. It's like a frustum of sand which is being pushed down into the clay. And it's got a sort of an inverted trumpet-type shape in that push-out. As you go below into the clay layer, you can see you're actually bringing a lot of sand down with you, and you have a much larger footing in that clay layer below. So if you want to predict what the capacity in the clay is, you need to account for the fact you've got this much bigger footing than what you thought you had, which again is not actually accounted for in the design guidelines. And that say is a punch-through. So that would be 8 metres of where you've got less load than you had at the top of the punch-through event. But I'm going to concentrate on trying to predict that peak. So so that's the visualization of what the mechanism is. We also did a very large series of centrifuge tests where we take the whole spud can and penetrate it here. We're using our top left-hand side here is our drum centrifuge, which is like a big washing machine where the soil goes all around the outside channel. So it's very good for these comparative type tests. And so here we changed the height of the sand layer and also the diameter, and you can see in that picture there different diameters of spud cans. And what we're trying to do is change the ratio of the height of the sand layer to the diameter of the footing. Here are just some example results. Maybe concentrate on the pink line here, the 6 metre diameter footing. You can see it has a very peaky peak load. It cuts off a lot and then picks up the load again in the clay layer. So we're trying to predict those peaks. Of course, as the diameter of the footing got bigger, the height of the layer to the diameter decreases, and you get a less of a peak that's occurring. The pressure that's needed is reduced. And just when we put all the results together with different sand layers, you can see we get a very consistent set of results for 30 or so tests. The challenge is when you numerically model this or try to come up with an analytical method, even though the sand was the same in the test, the relative density was the same, by changing the HS/D ratio, you're changing the peak stress, and therefore you're changing what would have been the operational friction angle and dilation angle that's occurring in the sand. So what we did is you could, if you took a finite element analysis like we did here, this is just using sort of an easy one like Plaxis, axisymmetric, you could adjust the operational friction angle and the dilation angle to try to match that experimental result. And that's what this is showing here. So that's the match for one particular case. It's sort of useful. You could do that for each of them, but it doesn't help you too much. What we eventually did was to, we bastardized the Bolton equations. If you see in Geotechnique in 1986, Malcolm Bolton comes up with relationships to relate the dilation angle, 0.8 of the dilation angle is the difference of the operational friction angle and the critical state friction angle. For those who know those equations well, you'll see that we've replaced the log normal of P dash with the Q peak here. So we're replacing it with what's the stress under the footing. That's why we're bastardizing it. But what we have here is a relationship that can relate the peak stress that's occurring with a prediction of the operational friction angle and the dilation angle. And so when you try to fit, and the graph on the left-hand side here shows the Q peak from the centrifuge tests against the Q peak from the FE analysis. And you pretty much are within 10% most of the time or 20% right. It's quite nice that we've now got some formulas to try to tell for these sort of punch-through conditions what the friction angle and the dilation angle underneath the footing are. And if you looked at the mechanism of failure from the FE, it's at about what that dilation angle would be. I'm just showing one example here. And that was also very consistent with the PIV, that even though it was a bit trumpeted, It tended to be when you had high stress, it's more vertical, no dilation. When you had less stress, it's about where the dilation angle would have been from these sort of predictions. So what we've done as the new model, it looks very much like the Hanno-Meyerhof and the punching shear. It's a mechanism, it's a friction resistance from the sand at an angle which is the dilation angle out from underneath the footing, plus the bearing resistance in the clay below. So you need to add the two up to get the prediction of the peak. Won't go through this in any detail, but basically it's a silo analysis. You take infinitesimal thin horizontal disks through that friction of sand. You can set up a differential equation of the vertical stress. So you take the stress at the top, stress at the bottom, and the friction along the sides. And again, the problem here is you don't really know what this friction along the sides is, or even what the normal stress is. So in the formula, we fudge this with a fudge factor. So we openly admit that. The dF there in that equation is just a ratio of what the vertical stress would be at any point compared to the stress at the side. And we had to backfit that against experimental data to know what that should be. Anyway, you can integrate that equation over the whole friction of sand, and you get what looks like a very complex equation. But when you break it down, it's sort of simple. It's the bearing capacity. The first term is the bearing capacity of the sand. Below, we have bearing capacity factors for that. The second term in that first bit of the equation is the resistance of the sand at the sides. And the big term is actually the weight of the soil itself. The more take-home message from that is that we now have a model where you can get all the parameters from very simple site investigation. It's important for offshore. You account for the behaviour of the sand itself. And if you look at this chart, okay, we're cheating because half of these dots are here are the model we calibrated for, half are just other experiments from around the world and in our own centrifuge. But you can see you get a better match between our calculated model and our centrifuge model, which are the blue triangles. The squares and the crosses are actually the ISO, the current guideline methods, which always tend to be under-predicting what the capacity is. And that's sort of a very known thing around the offshore industry, that these methods do that. How am I going, Tom? 5 minutes? Okay. The last area is renewable energy developments, and it's possibly where in sustainability we can make the greatest contribution technically as geotechnical engineers. Most of the developments in Europe at the moment are using that left-hand side slide here, monopiles to develop the wind farm. I believe that if England wants to reach UK wants to reach its targets, it needs to build another 6,000 of these before 2020, which is very ambitious itself. But again, most of it is using this type of monopile design. As you go to deeper waters, there'll be a trend, like there has been in the offshore industry, to go into floating systems. And there's a real chance, I think, for engineers to come up with cheaper foundation solutions to make this more economical development. Noting that even for the shallower waters, all of these developments have been government subsidised to make them economical. And also maybe throwing out that 61% of the USA's offshore wind resources are in greater than 100-metre water depths. So coming up with a floating system maybe is where we could put in some research effort. Some of the challenges here are that we've got a very large site to characterise. So in offshore oil and gas, you have one particular site, one very expensive platform to put in. Here we have thousands of very cheap platforms to want to put in over a very long site. And there's a real need and a real desire to have much cheaper site investigation to do that. And I Dogger Bank's in the UK, and that's the picture of how big that site is compared to, say, so you can see it's much bigger than the City of London. I tried to put that in the US context, and I believe it's 1.5 times the state of Delaware. But I believe Delaware's not very big, so maybe that's not a great analogy. But anyway, to try to get, there's a need for cheaper site investigation and also linking with geophysics to be able to link that together to bring costs down. The other massive challenge for renewables is that you've got a very light structure. Rather than oil and gas, you've got a very heavy structure. Here you've got a very light structure which has very large overturning moment and horizontal loads, with not only that, very stringent serviceability requirements. For instance, over its lifetime, you can't see much rotation of the turbine itself, less than 1 degree. So accounting for cyclic loading, where it's hundreds of thousands of cycles and how much accumulated rotation you get, is a huge geotechnical challenge. But the The good message here is that the costs of these foundations can be 15, 30, even up to 40% of the total cost of the turbine installation, the whole project itself. And therefore, there's much potential for geotechnical engineers to make a difference and make these economical to develop. And some solutions have come from the oil and gas industry, though in the paper we also make the point that that can also be hindering these developments because of the differences that are occurring between. So they basically used the knowledge to date, but this is also hindering, I think, some further development. There's been some very nice work on statistical methods for site characterization. Very good testing for a large number of cycles, particularly at Oxford University, where they've now got nice methods to predict accumulated rotation over tens of thousands of cycles. In bold, I think there's a large future in multi-directional loading for shared anchor points, which I'll talk about. And what I mean there is that if you were to build floating turbines and more than, say, in a traditional 3 or 4 point mooring system, you can already see that for 200 turbines, you've got 800 anchor points that you need to put in. If one could get arrangements where you could share them, and here's an example that was given in the literature by Brenton and Moe, where if you link the turbines together, have common shared points, you can drastically reduce the costs. Reduces the footprint, reduces the impact on things like fisheries and marine habitat. However, it's not a problem that's very well understood. Most offshore has been unidirectional and concentrating on cyclotic in that unidirectional way. And the example I'm showing here is some testing which was performed again at UWA, but with Melissa and her co-workers at the University of Maine. It's just an example here is it's cycling in the L1 direction here. And so in the same way with the SEPLA, we're cycling at 35% of what would have been the monotonic pull-out capacity. So it's going in L1. And then how is that affected if you now come into the L2 direction at 90 degrees? And the top figure here is sustained loading. The bottom figure is cyclic loading. And in both cases, you actually got an increase of about 50% of the capacity due to the cyclic loading that had occurred. Now, this is normally consolidated clay. You're getting nice consolidation effects that's causing that. But there's very little work in this multi-directional loading of caissons, and I think there's a great future in research in this area too, as again, try to reduce the costs and bring these things economical. Conclusions. I suppose I threw out the challenge that we're still going to be in an era of escalating energy demand. And I would think that geotechnical engineers have a really strong role to play, and I hope I made that point to meet some of these challenges and to meet the challenges of sustainability as well. I broke it into 3 areas of deepwater, new development regions, and offshore renewables. However, there's still many technical challenges, and if I could just summarise a few, that we're getting what I'm calling geotechnical transformations. That we used to be in design where things were static and stayed still, and we're now in the offshore looking at things that move a lot and things that go long distances, and that's taking new methods to try to design. A lot of cyclic loading problems still unsolved. Integrated wave structure soil modelling is a big issue, and you can see that from if you wanted to get that multi-directional wind farm up and running. You know, you've got integrated modelling that needs to be occurring between all of the different engineering types. And I'd also, though I haven't talked about it, would put in risk assessment into all of this as being quite important for driving down costs and making things more sustainable. Just to acknowledge my co-authors and also my colleagues at COFS who have contributed to this work, and of course funding bodies. And thank you again to Geo-Congress for the very kind invitation.